My talk today is going to be about algorithmic memory, and we believe it's a way to increase memory performance essentially by an order of magnitude. This is joint work with my friend, colleague, and everything incarnate and co-founder, Da Chuang, who's at our booth there, as well as, of course, a number of other folks at Memoir. So I'm going to jump straight to the chase here and sort of start with a graph that we've all seen. What you see here on the x-axis is time, and on the y-axis is performance. This is our standard Hennessy-Patterson computer architecture graph. You've probably seen this graph with the red and the green line. The red line is the aggregate processing speeds over the last 20 plus years. And the green line is literally external memory latency. And we've all seen the processor memory performance gap, where the processor was waiting for data to be picked from external memory. And so the difference between the red and green line was the traditional gap. And we, as sort of an industry in the SoC world, have tried to alleviate this gap by bringing memory on chip. And so the difference between the red and green has been mostly alleviated for SoC-based systems. And when we look at a processor today, it's essentially accessing tons of embedded memory. So if you look at the speed of embedded memory, we can look at the blue line, and you'll notice that embedded memory literally has been growing as fast as on-chip clock performance. Now, over the last 10 or so years, the red line's taken off from architectural techniques, instruction-level parallelism, multi-core processing, data path pipelining, so on and so forth. So we've almost seen about 20% growth in aggregate processing performance in the last 10 years. But if you look at embedded memory, there's been no such change. Embedded memory is literally dominated by the speed of a clock. And if you look at 45 to 28 nanometer and 28 to 14 nanometer, there's been less than 10 to 12% better frequency on embedded memories, especially in the ASIC market. And the gap's only getting worse. What's even worse is that embedded memory is accessed much more frequently. And so if embedded memory slows down, the aggregate processing performance will be affected even more. So we as an industry have to do something to alleviate this gap. And it's sort of interesting to understand, why does the gap even exist? Why is embedded memory so slow? And for that, we're going to use a standard clock diagram here. So this is, again, probably EE 101, where you see a clock, a read address, and a data bus to any embedded memory. There's going to be one access made to embedded memory per clock cycle. And data comes out, sometimes pipeline, sometimes in the very next cycle. With one operation per clock cycle, you're limited exactly by clock speeds. And if clock speeds are not going to get any better, what can we do to alleviate memory performance without touching clock speeds? Right? That's the fundamental question we're going to pose, and that's an answer that we're going to try and solve here. And the rest of my talk, I'm going to spend about 5 minutes or so describing a solution to this problem. And then we'll talk about some of the ramifications and benefits of this approach. So we'll start with what we believe is one way to solve this problem, and we call this algorithmic memory technology. So what we've drawn here is any standard embedded memory. Imagine this was an embedded memory used in an L1 cache or L2 cache. Perhaps you used it for a networking pipeline, a packet buffer, or a counters structure. Imagine this memory was 12K deep and 144 bits wide. I just took some random example here. The physical compiler would break this up into a bunch of banks. And if you run the clock at 500 megahertz, you would get exactly 500 million operations per second, and no more. You could be lucky, and data, you might access it from a different bank, and you might get more accesses. But embedded memory is built for worst case, and so you get no more than 500 million operations in the worst case if the clock here was running at 500 megahertz. What we do is we try to solve this problem by giving you more accesses in the same clock cycle. And that is shown in this animation here. So we add an orange block, and that's RTL. Hopefully it doesn't scare you because we're naturally not adding that much RTL. It's just a little bit. And this orange block also embeds a little bit of extra memory, which is hidden and not seen by the external user. What we've drawn here now is a dual port memory that's been given to the architect or the designer. So you get 2 ports. Each port is bidirectional in this example, and you can fire away both ports at the same time. Notice that even though the physical memory can only support 1 access per clock cycle, we're going to allow 2 accesses from this external interface. There's a bunch of salient points to this approach. The first point is that this emulation of a multi-port memory is done purely using RTL ideas. There's no circuit changes, there are no layout changes, we're not playing any voltage tricks, we're not overclocking the memory. So if we give you 2 accesses at 500 megahertz, the physical memory inside is not running at 1 gigahertz. It's running exactly at 500 megahertz. So somehow, by trick or sorcery, if you will, we're going to try and do multiple accesses even into the same bank. So we're going to allow 2 reads into this physical bank, perhaps 2 writes into this physical bank, and so on and so forth. The next thing we're going to do is that both these ports can access the entire memory address. There are no restrictions whatsoever on the addressing capability. Third, we allow simultaneous accesses to any row, address bank, or column. There are no exceptions whatsoever to the address pattern. So what's shown here in this diagram, if you view it as a black box, is a true dual port memory. If you build an algorithmic dual port memory and replaced it with something that used a circuit-based or transistor-based approach, with 8 transistors per bit cell, you could not distinguish the 2 memories. And that's the hard claim that we make with the technology. Last but not the least, we've spent a lot of time trying to educate the community that what we're doing here is not a trick or a statistical play, but it's completely deterministic, mathematically sound, as well as exhaustively formally verified. So we have strong adversarial analysis proofs using standard math analysis techniques to show that you can always post 2 accesses per clock cycle independent of the access capabilities. Similarly, we also use formal verification techniques to show that the IP that we ship, the RTL that we ship, has been formally verified and there are no corner cases. So that literally captures the technology that we have. And from this is going to follow a bunch of benefits of this approach. Now, important aspect here is there's no free lunch, of course. In order to make a memory faster, in this case, to go from 1 access to 2 accesses, we're adding some area. And a rough rule of thumb is that we add about 15% extra bits and logic totally to give you an extra port of performance. If you wanted to go to 3 ports or 4 ports, you would continue adding a few more bits and a few more gates to give this emulation. At Memoir, we build products that go up to 4x in performance. These are our standard products, but we can go all the way up to 10x in performance, of course, subject to implementation limitations of the RTL. So to recap, algorithmic memory looks something like this. You start with, let's say, a 2 megabit memory that you want. Say it's 32K deep and 64 bits wide. If you had only 1 port memories, you would get the diagram on the left. You could find 1 million operations for this 2 megabit memory. With the diagram on the right, we'll give you the same 2 megabit memory and give you 2, 3, or 4 ports in performance. Another key point about algorithmic memory, of course, is latency. We get asked this question all the time. Well, you're doing 4 accesses. Do you get all these 4 reads per clock cycle? Yes, you do. But what's the latency on these ports? And we built different algorithms. Some algorithms can actually have an additional clock of latency. And other algorithms actually give you 0 cycles of latency. Of course, there's a few gates that we add to the critical path, this order of the order of 100 picoseconds, which we squeeze, in most cases, within the same clock cycle, so that you get this emulation without having to pay any additional cycles of read latency. A quick thing in terms of usage and adoption, we call this the triple I slide. Nothing to do with ego, but just the three I's are easy to interface. We present the standard memory interface, so this looks like a standard SRAM. You can use it as a drop-in replacement for a multi-port memory. Readily integrate. We're using standard SoC design flows, so we can fit into any SoC, ASIC, or ASSP. And rapidly implement. You can use it on any process node or foundry, because what we ship is soft RTL. The next question to ask is, if you can increase performance by putting more bits, can you play the game the reverse way? Just, can you get a better memory, just more denser, but keep the performance the same? So what we're going to look at is this experiment where we've looked at a two-port memory. So this is one read port and one write port per cycle. The x-axis is the instance size of memory. So that's literally drawn in megabits. And the y-axis is the normalized density of the memory. So a quick thing about this graph is we've normalized the single port density to 1 megabit per millimeter square. So the standard 6-transistor cell lines up somewhere here in density. The graph that's drawn here is a standard two-port memory. This is a physical 8-transistor memory built using only circuit-based techniques. And any memory looks like this. It's got a bad density at the very beginning, and once you pass a certain capacity, you get a very good density. So if you took a two-port memory, you might get a density that dies off around 0.5 to 0.6 megabits per millimeter square. Right? What we do is we'll take the one-port memory, so we'll start with something that's much denser. So the same capacity as this one, but it's much smaller in area. We add an algorithmic layer in front of it, emulate the two-port functionality, and you get a graph that looks like this. So moment of truth here is, as you can notice, when the memory capacity is really small, an algorithmic memory is actually worse than a physical memory. So, and it's important to note here that the approach, or the algorithmic approach, is not a panacea. You do not want to use it for every memory out there on an SoC. The memory is too small. You will not get better area and power. But once you're beyond a certain size, the algorithmic boost gives you a better density. We can look at the 4-port memory, and the graph looks very similar. So the x-axis is size, the y-axis is megabits per millimeter square, and we've drawn the 4-port memory that's really tiny in density. In this case, no better than 0.05 megabits per millimeter square. Again, with an algorithmic approach, we'll take the 6-transistor cell, so we'll take the one-port memory here, and add RTL above it, and you get a graph that looks like this. So the more ports you want, the better is the area and power savings, because the circuit-only approach is much larger in relative area. Now, you're probably already wondering, if you can do this with area, could you probably do the same with power? Right? And the answer is very similar, with one caveat. So first, let's look at a simple power graph. This is the same two-port memory, but what we've plotted now on the y-axis is milliwatts of power dissipation. You'll notice that the algorithmic memory sort of kisses this curve out here, and then gets better only after a certain 1 megabit cutoff, if you will, in this case. And so the reason for this is very similar. Once your memory is very large, the static dissipation of the 6-transistor cell is much lower than an 8-transistor cell or a 12-transistor cell. So after a certain cutoff, you will actually be able to save power from an algorithmic memory too. But again, when you're very small, the additional logic that's added could actually make you worse in power. You can do the same for a 4-port memory, and you get a better curve. Now, all of these graphs that we've drawn are at a particular frequency. What happens if you increase the frequency of any of these graphs? It turns out you actually get better area and better power as compared to a circuit-based approach, because a 6-transistor cell can go the fastest in any process node. So if you look at a 28-nanometer process, you could get 1.2 gigahertz in performance from a 60 cell. Maybe a dual port only goes to 900 megahertz. So with an algorithmic approach, you can get a frequency benefit because we're building everything on the fastest and densest 6-transistor cell. Now, we'll move to a sort of holistic view of the algorithmic memory approach. And that's drawn in this diagram here. So what we've tried to capture here is three three different axes of memory usefulness, if you will. The x-axis is the memory density of a bit cell. The y-axis is the performance, the number of simultaneous operations you can pose to memory. And the z-axis is the power efficiency, so the megabits per milliwatts of a bit cell. If you look at a purely circuit-based approach, you might get a couple different points on this graph. The 6-transistor cell, which is a single port, lines up here. It's very dense. It's far ahead on the x-axis. It's not very fast, and so it can only give you one operation per cycle. So it's sitting at the bottom of the XZ plane. In contrast, a 4-port memory, if you built it with circuits alone, you could put 12 transistors together and get 4 axes, is very bad in density. It's probably about 1/10 the density of a single port. So it's sitting to the left of the x-axis, but it's very high in performance. It's 4 operations per cycle. So with physical memory alone, you'll see points in this space. With algorithmic memory, we're just building on the best physical memories and building out more memories as compared to a purely physical offering. So you'll get a bunch more points. For example, you might get a bunch of orange points that give you more performance. Like a point here, for example, gives you 6, 7, maybe 8 axes per clock cycle because they're built on top of these memories. You can get points that are much denser. So here is a 2-port memory that's built using purely a 1-port cell. And you can get points that are much more power efficient, and that's shown in green. So essentially, by adding the power of software to hardware, you've now created a whole suite of memories, giving architects and designers a lot more flexibility on what you can do with memory. The single point of this slide is to say that you can now view memory performance as a configurable parameter rather than as a fixed function point in the plane. In fact, it's interesting to notice these points here. The 2-port memory here is purely built using circuits, whereas we built 2 different 2-port memories. This one's slightly denser, this one's slightly better in power, and they're all built using these 1-port cells. In fact, you can get many more points on the space that have different area and power trade-offs as compared to a pure circuit-based approach. You can, of course, get a large portfolio of memories with this approach. So here we've shown more than 10 different memory compilers built algorithmically. And we see a lot of uses in networking and communications, as well as sort of data path buffers, L2, L3 caches, which need to be multiported. What's more interesting here is you find some esoteric memories. For example, you can look at a memory here that gives you 4 read ports or 1 write port. So what does this memory mean? Here's a memory that is really built for read performance. If you're mostly doing reads, like you've got an instruction cache, you occasionally do a write from DRAM, or you've got a lookup table in networking, which is 99% reads, we encourage customers to use a generator or an algorithmic memory that's optimized for reads. This is way more efficient than doing 4 ports that are bidirectional into memory. And the reason being is we have different algorithms that can increase read and write performance. So you use the generator that's most suited to your application. You can, of course, use it for other applications, such as L2, L3 tracks in microprocessor caches, graphics and video pixel structures, where, for example, 1 port here is bidirectional, that's 1 RW, and the other port here is a read-only, depending on what your application does. When we started looking at algorithmic memory, initially we started with something that was very simple. But over time, the complexity and the state space of solutions has grown. And so we built a tool to generate an algorithmic memory on the fly. So what's shown here is sort of a utopia for an architect, if you will. What's shown here is on the left-hand side is a sort of a GUI representation. This is the fake GUI. We have a real GUI and a demo if required. But the PowerPoint version of the GUI looks like this. You can specify the acceleration you want from a memory. You can specify the number of read and write ports. You can say, I want 2 read ports and 2 write ports into this memory. Specify your width and depth. Specify your latency. Do you want 0 cycles of latency? Or are you OK with giving it a couple cycles? And then specify your optimization criterion. So you could say, build me the most area-efficient multiport, or perhaps you want something that's more power efficient. And of course, there's intermediate points in between. So that's on the left side. On the bottom is the physical libraries that we import. So perhaps you wanted to use a TSMC process node. So you would import only TSMC physical memories here. Or if you use a Virage or an ARM or any other memory library, you would import only those libraries and would build an algorithmic memory that's specific for your requirements. A last question, if you will, here is something we always get asked, which is, does this work? Are there corner cases? Could you break? Are there bugs? Sort of very common questions that we get asked. And the way we sort of answer this is a two-pronged approach. So every algorithmic memory that's shipped is a combination of orange and gray. Orange is the RTL that we write. The gray is the physical memory. The RTL is formally proven as well as mathematically verified. So we're able to show exhaustive formal proofs so that every traffic pattern is covered. So this is stronger than a test chip where you can run a billion patterns. Here you can actually show that every pattern is actually covered. The gray part is just your physical memory. So to us, physical memory is a pass-through. We expose all the physical memories at the top level. So you can do your own DFT, you can do your own BIST, you can do any testing that you did on your physical memory. In fact, the reliability of a physical memory is done by the vendor, and we play no part in that. What's interesting about this diagram is the bottom line here, which is if you wanted to build, say, a 4-port memory, you don't need to use a 4-port BIST. You would continue using a 1-port BIST because we make sure that no tile of memory is used more than once per clock cycle. So continuing to use a standard 1-port BIST, you can test 2, 3, 4, or any n-port memory. I'm going to sort of, before I conclude, sort of end with an example to show you some of the ramifications of this approach. And what's shown here is an example from one of our customer evaluations. This was from a large vendor in the communication sector. So they had a chip that was almost 24 by 24 when they did an RFQ. This chip had almost 800 megabits of memory, more than 165 unique instances of memory on the chip. And they wanted a few multiports, 4 reads to do lookup tables, 1 read and 2 write to do data path buffers, and a bunch of other requirements. When we looked at this memory, we were able to reduce its footprint by almost 20+% on this chip. So we took a bunch of these 2-port memories, 1 read and 1 write, and converted them to 1-port memory. In fact, we were able to convert some of these to 1-port embedded DRAM, and that gave a big boost in terms of area and die savings. There were other blocks that we were able to accelerate and just build multiports for. So on this particular chip, the area and power savings was almost 20+% and almost 12 watts in die savings. Now, moment of truth, this is, of course, not always possible. Different chips have different requirements. In some cases, the area savings are much smaller. And in terms of multi-ports, of course, requirements differ based on the application space. But this is just a way to show you the possibilities that are possible with an algorithmic approach. I'm going to conclude with sort of a quick summary and sort of a thought statement, if you will. There's 5 benefits to the algorithmic approach. The first, of course, is improving ports. That's the bread and butter of algorithmic memory. You want more ports into memory, you can use this approach. Along with more ports, you also get better clock frequency because we're building 2 ports and 4 ports from a very fast single-port memory. The second benefit is sometimes you can lower area and power, provided your memory is at least a certain size. A third benefit is you can easily integrate and use it on a standard SoC process. We can help create a versatile portfolio of memories. So you're no longer stuck with 1 or 2 kinds of memories, but you have more than 25 different types to choose from. And finally, you can reduce your cost as well as risks and even time to market based on if you want some of these multi-ports much faster than when they're built by a vendor. So the moment a vendor builds you a 1 port, you can now build a complete chip and a whole portfolio of memories. So I want to end on a couple key observations. The first thing is everything we've done here at Memoir, each approach that we've used to make reads better and writes better is not unique. Every idea in computer science has been known for the last 30 years. And when we look at any single technique, I guess Di and I laugh about this almost every day. No technique is new. It's been known, it's been out there. What we think is novel here is the way we have put everything together. How do you put algorithms for reads and writes and caching, load balancing? How do you manage memory coherency so that you can build a sort of clean and beautiful multiport that designers can use without any headaches? So that's where we think the uniqueness lies. And the second thing here is, I'd like to end with an analogy. Processors faced exactly the same problem 10 years back. To increase performance, the only way out was to do parallelism. And so multi-cores started almost 10 to 12 years back with the promise of increasing processing performance. And we've done the same for memory. We believe that with clock speeds slowing down, the way to get more performance is by doing multi-porting. And we think of this approach as sort of a second hammer, if you will. Rather than just use circuits, let's use a second hammer and build something that's even better for end customers. Thank you.